might say something about the drift velocity, because we had said previously that current, the electrical current, okay, is equal to the charge number density, the number of charges per volume, times area, times the charge, or technically this should be like Q, the charge per charge carrier, times the drift velocity. Now, that number right there is normally E. So that quantity is normally E. It's normally electrons that are moving, or it's ions, singly ionized atoms. It's possible you could have a doubly ionized atom, in which that case that could be 2E. So it could be a variety of things. Your book assumes it's primarily just electrons, so this is going to be N, A, E, and then V sub D. Now, V sub D is the drift velocity. And so this is the average speed. Now let's think about that, because I wanted to mention this a little bit, because you've got a wire or some kind of conductor, and you've got a bunch of atoms in here, and each atomic core is basically in the way of any electrons that are moving. You apply an electric field, so we apply an electric field that way, and then electrons try to move to the right. And so they're going to be moving along, they'll be accelerating. We know that F equals QE, so in that case, this is going to be equal to EE. Okay, so that's the force. And so they accelerate, and as they're accelerating, they don't go forever, they bounce off of something, because they're eventually going to run into something. And then they bounce off, come over here, bounce off, come over, bounce off, and so what they do is they keep moving back and forth, accelerating for a while. And so we know F equals ma, so ma equals ee. So the acceleration is going to be ee over m. And so what's the drift velocity? Okay, the drift velocity, we know that velocity is v naught plus at. Assuming they start from rest, v equals at. Okay, now, if we imagine that there's an average time that it takes to go before it runs into something, then that's going to give you a velocity. So we define a characteristic time. Now, the characteristic time, tau, this is really half the average time, but because we want to find the average velocity. And so what we do is we say that V sub D is a tau. And this is going to be the average velocity of those, that's going to be the average velocity of all of those individual atoms, electrons moving along. So that would give you the drift velocity goes into current. Well, A is EE over M, so times tau, and so that gives you the drift velocity. So that means that the current would be N, okay, times A times E times EE over M tau, or in other words, N E squared A E tau over M. Okay. Current density is I over A, so the current density would be N E squared E tau over M. And so this would give an expression that relates the current and current density to what's happening at the microscopic level. It depends on the number of charges, free charges per volume. Depends on the charge of those free charges right there. Again, for electrical current, we are normally talking about moving electrons, so that's just E. Depends on the mass of the thing that's moving. Again, normally that's going to be the mass of an electron. and it depends on the average time between collisions. That depends in part upon several factors. One, it depends on the material property. What is it made out of? But also, even if you have a conductor like copper, you manufacture copper on Earth. Earth has an oxygen, nitrogen atmosphere, so you often have contaminants in the copper. And so that means those get in the way and interfere with the nice lattice structure that you normally would have of copper atoms, and that interferes with the path of the electrons. More contaminants typically means that you're going to have less current. And so that gives us an idea of what's going on. The other thing that happens is that with your atomic cores, if you heat it up, they move around more, and that gives you more chance for collisions. So more chance of collisions means smaller tau, which means smaller current. And so again, we have several factors that influence the amount of current that you have. And then the other factor that influences it is the electric field. Bigger the electric field, the bigger the current. We know the electric field is related to voltage. So that means if you increase the voltage on your conductor, you're going to have more current. If you decrease the voltage, you have less current. And that turns out to be very closely related to this concept right here that we're talking about. And so this gives us an expression really that's an interesting sort of thing, because what we realize is that the current is going to be very highly dependent on what we're doing right here. And in fact, we can say that the current is going to be proportionate to the electric field. Okay. And so what we do is we actually say that we solve here for the electric field. And so the electric field in here is going to be equal to J times M over N E squared tau. Okay. And so we would say E equals rho J. Okay, this is a lowercase Greek rho, and we call that resistivity. So the resistivity is going to be related here. So E equals rho times J, and that's going to be the resistivity. And so electric field has a vector, the J has a vector. Okay, and so that's going to be an expression here that turns out to be very interesting. Because we know that J is I over A. And so if we have a conductor here, it's got an electric field in it, okay? If the conductor is some length L, okay, then we look at what the expression we just had, you know, E equals rho J, where if you look at it, rho is going to be the M over N E squared tau. Again, we call that resistivity. And that resistivity is going to be related here to the J. And so what happens is if I multiply E times L, that's going to be my voltage. So that means if I multiply both sides by L, okay, then I have that EL equals rho LJ, or EL equals rho L over A times I. Okay, and so this is voltage. So I can define this quantity right here as something else. So V equals rho L over A times I, so I can define that to be something R that we call resistance. So this is our definition of resistance. So V is going to equal IR. Okay, where R is this rho L over A. Rho is a property of the material. Remember, the rho was m over ne squared tau. So the m is the mass, the charge carried, the electrons. The n is the charges, number of charges per volume. The e is the charge on each of the charge carriers. And tau happens to be the mean free time between collisions. Okay, and so that's and that is actually dependent on the temperature. So that means rho depends on the temperature. So this turns out to be a really interesting sort of relationship right here. All right, so that we call Ohm's law. It was actually developed by George Ohm, and he didn't really know what he was measuring. He just knew that you have a voltaic pile. So this is this alternating pile of metal and wet paper. The bigger it is, the bigger the voltage. Now, he didn't really understand what was happening, but it turns out that we were getting a small voltage for each one of these. And so the bigger the pile, the bigger the sum voltage. Basically, he was putting volts in series. Okay, and then he connects this to something here, some conductor, but the conductor is not perfect. And so he calls it a resistor. And then current would flow. And so he realized the bigger the voltaic pile, the bigger the current. The bigger the resistance, the smaller the current. So he defines this as V over R. So this is how George Ohm wrote it, but in textbooks we almost always write it V equals IR. Okay, and so the units here, volts, again, they didn't know what they were measuring. They just knew the bigger the voltaic pile, the more volts it had. We now know volts is joule per coulomb. Current was measured in amps, and they didn't know what an amp was, an ampere, Andre Ampere. But the bigger the current, the bigger the amps. They later figured out an amp is a coulomb per second. And then resistance was measured in ohms. The symbol for an ohm is a capital omega. So you might have a resistor here, and the resistor might be 125 ohms. So that just should be an example right here as to how you would define that. And so this now gets us the idea of how at the microscopic level you get this. Now, should point out that frequently